Hey guys, in this lesson we're going to be going over the vector and Cartesian equations of a sphere. And I've written both the vector equation and the Cartesian equation of a sphere up here, so you might want to copy that down to reference later on. You might also notice is that the vector and Cartesian equation of a sphere is very similar to that of a circle, except we've just added in the third dimension, or the z-axis over there, and it's still, the center is still going to be A, B, and C, with the radius of capital R over there. Let's just have a look at what the sphere looks like in 3 dimensions. So the red axis over here is my x, the green is my y, and the blue is my z axis over there. And this bit over here is the actual sphere itself. Now what you've noticed is that I've got this yellow line up here. That's actually the vector equation of a point R that lies on the sphere. And what you'll notice is that any point R, if I go around the sphere, the distance to the center, doesn't matter where my R value is, the distance to the center is always going to be the radius. That's why we say the modulus of R to the center equals the radius, where C is the center up here. You can also see that from any angle, as I go around the sphere, the cross-section of that sphere looks like a circle. And that's really important when we're solving problems to do with spheres, is that we'll treat them like a circle. Alright, so just coming back here, that's the sphere we were looking at before. And also just notice the similarities between the vector equation and the Cartesian equation of a sphere, and the vector equation and Cartesian equation of a circle. They're very similar, we just add in that third dimension. And as mentioned before, we can think of any sphere kind of like a circle. If we cut the cross section through the middle of the sphere, we should get a circular shape. And any point R on the outside of this sphere, the distance from any point on the outside to the sphere to the center of the sphere is the radius. So that's why we still end up with the modulus, or the length of any point on the sphere to the center must equal the radius. Alright, so let's just do a few questions now. Determine the vector and Cartesian equation of a sphere with center 5, negative 3, 2, and radius 6. So we need to do the vector equation and the Cartesian equation. So the first equation up here is my vector equation, and the second equation will be my Cartesian equation. So it's pretty simple. We've just got the length of R to the center. In this case, the center is at 5, negative 3, and 2. The distance of R to the center must equal the radius, and the radius is 6. So that's my vector equation done, and now we need to write out the Cartesian equation, which is just this form over here. So it'll be x to 5 squared plus y plus 3 squared. It's a positive 3 because a negative and a negative makes it a positive 3, plus z to 2 squared equals 6 squared. So x take a squared plus y take b squared plus z take c squared equals r squared over there. So that's my Cartesian equation done. Nothing too tricky about that one. Alright, question 2. Determine if the point 1, negative 2, 6 lies on, inside, or outside the equation r2, 1, 0, 4 equals 3. So we know that this sphere has a radius of 3. So if this value that we want, so if our 1, negative 2, 6, that's the R value. So if that point there to the center of 1, 0, 4, if that equals 3, then it's on the sphere. If it's less than 3, then we're inside the sphere. And if it's greater than 3, then we're going to be outside the sphere. Because the distance of the point to the center, if it's bigger than 3, that means we're outside the sphere. Alright, so let's just work this one out here quickly. And that's going to give us the modulus of 1 take away 1 is 0, negative 2 take away 0 is negative 2, and 6 take away 4 is 2. Now we need to find the length of this vector. The length of that vector is going to be the sum of the square of each of its components. So 0 squared is 0, negative 2 squared is 4, 2 squared is 4, which gives us 2 root 2, or the square root of 8. Alright, so let's see what 2 root 2 looks like inside the calculator. So I'm going to go 2 root 2, make sure that you're in decimal mode. And when we hit execute, that's 2.828. So we know that 2.828 is less than 3. Now, remember I said if the value equaled 3, we'd be on the sphere. If it was greater than 3, we would be outside the sphere. But because we are less than 3, the point, therefore the point 1, negative 2, 6 lies inside the sphere. Just quickly, why is that again? That's because the distance of the point to the center is smaller than the radius, so we must be inside the sphere for that to happen. Alright, question 3, determine the minimum distance between those spheres with those vector equations. Alright, for these questions, I like to draw myself a nice picture. And again, whenever you think about spheres, just draw them in 2 dimensions, because the concepts will be the same in 2 dimensions as their own 3 dimensions. So I'm going to say that this has got the point 1, 1, 1. And the center of this sphere is negative 4, 3, negative 5. And the first thing I'm going to do is I'm going to work out what's the distance between those 2 spheres over there. What's the distance between those 2 centers? So we need to first find out what this vector is, and we can do that by subtracting the 2 centers away from each other. So we want to find the length of the vector 1, 1, 1 to the vector negative 4, 3, negative 5. And when we do that, we end up with the length of vector 1 take away negative 4 is 5, 1 take away 3 is negative 2, and 1 take away negative 5 is 1 plus 5 is 6. Then we need to find the length of this vector. The length of this vector is the sum of the square root of the sum of the squares of each of the components. So 5 squared is 25, 2 squared is 4, 6 squared is 36. And when you add all of those together, 25 and 36 is 61. That's going to be 65. And we'll take the square root of 65 there. Now we also know that the radius of this sphere is 1. So that length there is going to be 1. And the radius of this sphere is 2. So that distance there is 2. So we don't want the whole length. We just want from there to there. So we just want the edge of the sphere to the edge of the sphere over here. So the distance between them, the distance is going to be the square root of 65, take away 1, take away 2. So we're going to take away 3. Alright, and then if we wanted to convert this root 65, take away 3 into a decimal, we would just type it in as root 65, take away 3, gives me 5.0622 decimal places, so equals 5.06. So the minimum distance between these 2 spheres is going to be 5.06. Now, how could we have done that quicker in the class pad? Well, I could have gone action vector norm, because norm gives me the length of the vector, and we want the length of the fraction of 2 vectors, so we're going to do 1, 1, 1, take away negative 4, 3, and negative 5. And when we do all of that, we get 8.0622577. And when we subtract 3 away from that, we get our 5.062, which is what we had before. Alright, let's move on to the next question. Find the minimum distance between the line with that equation and the sphere with this Cartesian equation over here. Now, to solve this problem, I'm just going to draw a picture for us quickly. So what we've got is we've got a line coming up this way, and we've got a circle down here. And what we're looking for is the minimum distance from this line to this circle. Alright, so we want to find out what that distance is over there, this perpendicular distance. So it's almost at a tangent to the curve. If we drew the line parallel this way, it will touch at a tangent to the curve over there. Now, I'm just going to extend this line. The shortest distance from any point to a point on a sphere or a circle is going to go through the center. Okay, so what I need to do first is we need to establish what the direction of this line is. Well, the directional line is given us up over there, 1, negative 1, 0. So this line's going in 1, negative 1, 0. Now, at some value lambda, we're going to have this point M there. All right. So the point M is going to have the position vector of 1 plus lambda, 4 minus lambda, 3 plus 0 lambdas, which is 0. So remember, the equational line can give me any point on the line. And I'm just saying for some value lambda, I'm going to have this point M here, where M to the center, the distance of M to the center is going to be a straight line. And it's also going to be, it's going to go through the sphere such that it's at 90 degrees to the sphere. So let's call the center of the circle 0 to negative 3. Right, because I got the 0 there because it's x take away 0 squared, negative 2 and negative 3 because it said take away negative 3. So the center of the sphere is going to be 0 to negative 3. So I'm going to call that point C there. So if I'm going from M to C, that's going to be point C subtract point M. So it's going to be 0 to negative 3. That's my C vector. Take away my M vector. My M vector is going to be 1 plus lambda, or take away lambda and 3. When we subtract those two away from each other, we're going to get minus 1 minus lambda. 2 take away 4 is going to be minus 2 plus lambda. Negative 3 take away 3 is going to be negative 6. Now, we know that the vector MC must be perpendicular to the direction of the line. So we know that MC dots the direction of the line, which is 1, negative 1, 0. That must equal 0 because those two are perpendicular, and a property of perpendicular lines is that the dot product equals 0. So when we take the dot product of MC and 0, what we end up with is 1 times minus 1 minus lambda is going to be minus 1 minus lambda. Minus 1 times minus 2 plus lambda is going to be plus 2 minus lambda. And then 0 times negative 6 is 0, and that's all got to equal 0. So this is the result of the dot product, and it all equals 0. Now when we solve this, we're going to have 2 lambda equals 1. That means that lambda is a half. So when lambda is a half, we know that we can find our point M now. And we can actually find out the length of MC. So let's substitute lambda equals 1/2 into our MC equation now. Remember, going from M to C. So our MC vector is actually going to be minus 1 minus 1/2, so it's minus 1.5. Minus 2 plus 1/2, so it's minus 1.5. And minus 6. Now, we don't want the vector MC, we want to know what the length of MC is. So we're going to go the length of MC. Going to be, and I'm just going to use the class pad for this now. So we're going to go the square root of 1.5 squared plus 1.5 squared. Oh, where's my squared button? Plus 36. All right, and let's go to standard form, and that's going to be 9 root 2 on 2. So the length of MC is going to be 9 root 2 on 2. But just think to yourself, is that the minimum distance of the line to the sphere now? Well, no, it's not. We've actually gone into the sphere. We just want to touch that point on the end of the sphere over there. So what was the radius of the sphere? The radius of the sphere was 1/2. Remember that this quarter is actually r squared. So to get rid of the r squared, we'll square root a quarter, and that gives me 1/2. So the minimum distance is actually going to be, and I'll do this in a different color so you can see what I'm doing. The minimum distance is actually going to be 9 root 2 on 2, take away 1/2. And that's the minimum distance there because it's the length of this vector, subtract the radius of the sphere.